Today's first talk, and that's Claudia Scheimbauer, who will talk about dualizability in the higher Morita category.
So thank you very much. Thank you very much for the invitation, and thank you all for coming on Friday morning after the last evening. I appreciate it. I hope last night was fun, and I'll try to be gentle. So what I'm going to be talking about is dualizability. So maybe let's go gentle first. We've heard, this is something you all know, so I did my homework and pre-wrote it. So the first notion that we will want to talk about is, well, we have already seen it quite a bit, adjoints. But now we will be talking about, well, we have two categories, C and D, and we want to have an adjunction. So L is a left adjoint to R if there exists a unit and co-unit such that these identities are true. We saw that in Emily's talk. And the other notion that we would like to somehow talk about and generalize later on is a vector space having a dual. So a V star is a dual to V if there exists an evaluation map and a co-evaluation map, such that, well, if I compose in this way, we get identities. So this is hopefully nothing new to you, but somehow we will want to look at generalizations of these notions in higher categories. I don't know if this is a good color, but let's try. So here we were working in the bi category or two category of cats, of categories, functors, and natural transformations. And well, we can try to replace that by an arbitrary two category B, or bi category B. And now we take this here, these two to just be morphisms in our bi category, and ask for two morphisms as such that the compositions are identities. On the other hand, down here, we were working in the symmetric monoidal or just monoidal category vect of vector spaces and linear maps, and we can try to generalize this to any monoidal or symmetric monoidal category. Well, now we replace this by an object in C and this by an object in C, and these by morphisms. Here's the tensor product that I'm using, and read off the exact same definition. Okay? So these two notions make sense in any monoidal category or bi category. Maybe I should write that here. So somehow the goal for today is to discuss the generalization of this, and this has shown up in other talks, so I'll mention it later, in a very particular example, namely a higher Morita category. All right. So before I tell you which higher category we want to look at, which particular example, let's do some examples to test these notions, to understand what we can expect somehow for these situations to hold. So what other examples do I want? Okay, I can look at the following. Do I want to enumerate them? Maybe. I can look at something I will call ALG. ALG is a monoidal category and has as objects algebras. So I will try to follow my convention here and always write objects at the top and then go down. Sometimes maybe I will forget and go up instead, but I don't want to write out objects, morphisms, etc. all the time. So objects will be algebras, K algebras. And a morphism from A to B will be an AB bimodule. And to be precise, if I want this as a category, I have to take isoclasses of here. And what's composition? Well, if I have an AB bimodule M from A to B, and an BC bimodule n from B to C, then composition will just be the relative tensor product. Which gives me an AC bimodule. So that's the Morita category. And now here you can test what's symmetric monodal structure. It's just tensor product over K. And now exercise is that every object A has a dual. And the dual is very easy to write down. It's just the opposite algebra. And the evolution and coevolution are given as by A itself viewed as a bimodule in different ways. All right. So what about another example? Another example, let's take vect, but let's take pointed vector spaces. So now my objects are, well, a vector space together with a distinguished element in it. So you can think of it as a map to V just by picking out V. And now an exercise. Maybe we should start with the unpointed version going back to here. I hope most of you have seen that a vector space has a dual if and only if it is finite dimensional. So here finite dimensionality comes in. This is because you need a coevolution map to exist. And so now here the exercise is that if we add this additional data of pointing, so my morphisms, I want this to commute on the nose, then the exercise is that dualizable objects are the one-dimensional vector spaces. So somehow reduced to the trivial thing, to the monodal unit. Okay, so these two were examples of the lower definition. What about the top definition, having an adjoint? Well, let's continue, maybe, or maybe this should be called B, the second part. Now, this category of algebras that I wrote up there is actually a bicategory. So here I put AB bimodules again. Now without isomorphism classes, and then I can put homomorphisms of bimodules at the top. So we saw this bicategory. It was even a double category in Emily's talks. And now the claim is that a bimodule like this has a left adjoint if and only if M is finitely presented and projective over A. So you see now there's this one-sided condition showing up. It just depends on A. It's independent of B. And it has a right adjoint if and only if the same thing holds over B. All right. So this is a nice exercise to do. So now let's see what we can do for higher categories. So the main place I want to go is I want to find a infinity n generalization of this and then show similar statements, well, at least to one for now. Okay. Yes. Okay, so we've seen several talks about infinity n categories so far. I will talk a bit later working on a particular model for one, for the particular example that we want to check. But in general, I will give the definition a little bit informally. So we've seen this. So an infinity n category has objects and then morphisms between objects and then morphisms between morphisms and so on to n morphisms. And then it keeps on going. I don't want to write, but this will be invertible up to homotopy. So we can do two things. So one thing that we can do from such a thing is we can truncate somewhere by discarding non-invertible higher morphisms. So we can truncate. Actually, I will only need the two truncation to kind of extract this part here. So we can get, maybe let me call this C, an infinity 2 category. Or even similarly to what Emily was doing, from there we can do a homotopy category and get a bicategory. I will just call this H2 of C without this truncation in the middle. The other thing I can do is that if C is symmetric monoidal, I don't want to recall the details of what this is, but what I want you to remember or to think about is that we can do a similar truncation as over there, but just to get a category, H1 of C, and this again will be symmetric monoidal. So we have a way of, from an infinity, symmetric monoidal infinity n category, to kind of reduce to situations where we understand our notions of dualizability. So now, definition. Yeah, maybe here. Right, and so now I will say that an object is dualizable in C if it is dualizable in here. And I will say it is a morphism has an adjoint if it has an adjoint in here. So I will use these, reduce it to the classical cases. So now definition, we start with a symmetric monoidal infinity n category. Then we will say C is fully n-dualizable. So sometimes, just as a remark, sometimes this is called C has duals. But I like to keep the dependence on n here, because this a priori, this could also be a higher category, an n plus m category. If two conditions, every object X has a dual in the sense that I just described over there, and two, every k-morphism for 1 less than or equal to k less than n has a left and right adjoint. So here maybe I have to tell you how to get the condition for k. Well, so I can pick out the layer of C that has somehow k minus 1 morphisms, k morphisms, and k plus 1 morphisms. And that part will give me, sorry, maybe let me take F from alpha to beta. This is my k morphism. So alpha and beta themselves are k minus 1 morphisms. So alpha and beta and hom C from some source to some target. So this here now will be an infinity n minus k category. And now I can play the same game as here, truncate and check. So we have these definitions. All right, and now any object x in such a C is called n-dualizable. So if you remember in Chris's talk yesterday, this came up as the conditions for the cobordism hypothesis, and that's exactly the motivation for getting this result. So maybe a last definition for an arbitrary symmetric monoidal infinity n category. There is C, which I will denote by ND for n-dualizable. The subcategory where, so this is somehow the universal thing that is n-dualizable that sits in C. And you can think of it as a subcategory whose objects are n-dualizable and morphisms have left and right adjoints. Which again have left-right adjoints and so on. So this is a bit tedious to write out, but this definition for us will be enough. Okay, let me recall our motivation, which can go, this one can go.
Is there an analog of a thing like that if C were an infinity-infinity category instead of infinity-n?
Depends on what you mean by infinity-infinity category. If by infinity-infinity category you mean a tower of infinity n categories that it sit inside each other, well, you can ask for in each of these parts for it to be n-dualizable. Yes, I know of such an example. That's Rune's co-span category, or span category. That can be realized as an infinity n category at every level, and it will always be n-dualizable.
I guess the reason I'm asking the question is it seems that to identify what's in C and D, you start from the top and then work your way down. Is that right? Because the structure maps that would witness dualizability of objects would then have to satisfy dualizability conditions.
Yes, that is true. That is correct. You kind of throw out somehow the things at the top and then throw out the next ones, etc. Yeah. Other questions?
Yes, I don't understand when you say any object X in such a C is called n-dualizable.
Yes.
Just by virtue of being in there, or with which?
Yes, absolutely. So this here is as dualizable as it can be, and any object in such a thing I call n-dualizable. For a general symmetric monoidal infinity n category C, I can find an fully n-dualizable part in here. So this is
not a full subcategory, right?
No,
Morphisms
this is not a full subcategory, yes. So this is fully n-dualizable, and the universal such thing. So now if I start with an arbitrary symmetric monoidal infinity n category, to say an element X is n-dualizable, it actually has to be in here. And all the morphisms witnessing the junction have to be in here. Let's see. So, right, the motivation, of course, is the cobordism hypothesis, which we've seen at the board yesterday, which says that if you take any symmetric monoidal infinity n category and look at symmetric monoidal functors out of it, or fully extended TFTs, then you can evaluate at a point, and you land actually in this n-dualizable part. But it says more. It says that this is an infinity groupoid, and this becomes an equivalence of infinity groupoids. So in light of finding TFTs, constructing TFTs, a non-explicit, non-constructive way is by choosing your favorite target category C, finding the n-dualizable part, and then choosing any object in there. Okay. So let's do this for a particular example. So informally, the example that I want to look at, and I will give a definition later, a precise definition. We want to look at alg n. So what is this? This will be the higher Morita category. So this here will be some nice infinity 1 category. You can keep in mind something like chain complexes or even vector spaces, but also nice cat, somehow, k-linear categories. Something like this. And then we have, this is, will be, right. Now I can take my objects, will be the EN algebras that we saw in Catherine's talk yesterday. And I will give a more precise definition of exactly what I mean by this. But this is somehow what we really want. One morphisms, if you remember in Catherine's talk, an EN algebra could be also seen as an EN minus 1 algebra. Sorry, an E1 algebra in EN minus 1 algebras. So I have an E1 direction, a chosen E1 direction, and now I look at bimodules for this, which are still EN minus 1 algebras. Two morphisms. I still now have my EN minus 1 directions. Can split off the first one, look at bimodules for this. And I can keep going. So I have n directions I can use up in that way. And now at the top, somehow I have used up all my directions, but I can kind of do two different things here. I could just say in S, or I could say of E0 algebras. So pointed guys. So keep a point. And then at the top, m plus 1 morphisms, I can do homomorphisms similarly to as we had up there. So up there is somehow the situation for n equals 1. E1 algebra in vector spaces is just an algebra, and I can look at bimodules. Well, there's nothing left already because I have n equals 1, and then I have homomorphisms. Okay, so the situation up there is this choice here. The other choice would be to consider pointed bimodules instead. Bimodules with a chosen point. Okay. So there are different ways of formally defining this, as I said before. One way, in this case, Rune Haukseng has a construction of this using generalized infinity operands. And this one here was part of my PhD thesis, and that's the one that we will discuss in a second. But I also said, like, maybe I would like to put in something like categories. And if you want to put in something like categories, this is actually two categories. I could not only use homomorphisms here, which are one morphisms in S, but I could also kind of put n plus 2 morphisms, etc., using the two morphisms if I have them. So if I have an infinity k category, I can keep going and get an n plus k thing. this is a lot of data. This is a bit overwhelming as it is. However, I wanted to have the informal description at the board before going into the rigorous details to be able to state the main theorem. Oh, I should say, sorry, this extension here was joint work with Theo Johnson-Fried. So now the main theorem that I want to talk about in this talk, which was joint work with Owen Gwilliam, is that alg n, maybe I will give this a name. Yeah. Alg n of S in the sense of this lower thing is fully n-dualizable. Okay. So why do we care about this? Well, an immediate corollary using the cobordism hypothesis is that every object A determines a fully extended NT of T. All right. So,
sorry, this is a case of the generality you mentioned before, where n dualizable is in an infinity n plus
category.
What is an alg n S an infinity n plus 1 at least?
Yes. Okay. I look at the truncation. Absolutely. You're correct. I should have maybe said n plus k here to match up with what happens over there. Thank you for.
Right, and so the meaning of that statement is if you throw away the non-invertible n plus 1, n plus 2 more
absolutely
dualizable.
Exactly, yes. Thank you for the comment. So what we're doing here is we're throwing away, we're forgetting that we have higher morphisms here. Just look at this part, and just as such an infinity n category, it's fully n-dualizable. So why is this good or bad? Well, it's good because we somehow got fully extended NTFTs. It's maybe not so satisfying because you might like to know what the NTFT actually evaluates to. So in this situation, this is actually explicitly given by taking factorization homology. This is the A version of factorization homology from John's talk. You can really explicitly write this down as a fully extended NTFT. For these purposes, so alg n is a nice target, as we see up there. If you think of A and B being K, what you get are A, B bimodules will just be vector spaces, and homomorphisms will just be linear maps. So this alg has the feature somehow that we recover vector spaces at the top. And Rune said yesterday that this is somehow a feature that we would like to have for targets of TFTs. So one could play the same game and put Rune's higher category of higher categories here. But since that's new and hard, I'll start with this one first.
So does the corollary depend on the cobordism hypothesis, or do you have an independent construction of this factorization homology in this special case?
So using the theorem as a corollary, it depends on the cobordism hypothesis. However, previously in my thesis I constructed this explicitly. So somehow we, now having this theorem and the construction from before, it's somehow a test of the cobordism hypothesis in some sense. It illustrates the two sides. Okay, but somehow, if we think again of the example up there, what we've been using somehow is only the lower two parts. But I said just before, actually we want to have vector spaces at the top and linear maps. So actually we would be looking for two dualizability, so 1 plus 1 dualizability. So here we would actually like to have something like n plus 1 dualizability, or even more. However, and this is the second part, again with Owen, So in this pointed version, only algebras which are equivalent to 1 as En algebras are n plus 1 dualizable. So this is not good. We would like to have non-trivial examples. So this shows that, okay, for the lower dimensional part, somehow this alg n with these points is good to see the n dualizability, but it's not good if you want to go higher. Okay. So what can we do? So remember, this was I'll add for now a pointed here. Unpointed. So basically, you should have a symmetric monoidal functor like this, which just forgets the point. So like philosophically, this should not be a big thing. At the moment, we don't have this, however, because just for technical reasons, nothing actually mathematical, just for technical reasons. But if you have that, nothing. It's not, I didn't say it's easy. I said the heuristic is easy, but the technical construction is not, because this and this were defined in very different ways. But if you had this, and hopefully we will have it soon, is that then you get the corollary as well for this unpointed thing, where you can actually go up, and which is more interesting for TFT applications. All right, but that's a conjecture. So, questions so far?
Description of the n plus 1 dualizable objects in the further category?
Not yet. So there are, and this will be the applications that I will tell you about now, there are examples where this has been done. So first of all, maybe I should say, if you look at this category here, you can notice, let's test our definitions. We said before, every object has a dual. That's great. But then we had the second condition, which I think I erased, for having, oh, it's exactly here, for having two dualizability, we get a condition. Okay, because not every left and right adjoint has, not every morphism has a left or right adjoint. So this somehow is similar there. We get the lower part, we get this like lower part here, every object has a dual, but we do not, and this will be finiteness conditions going higher. So examples, I said S equals vec is something you should keep in mind, or maybe chain complexes. So if we take alg1 of this, if we take vector spaces, we just get back the thing I erased. So what it means, so one dualizable, where's my table? Yes. So n equals 1, so every object is one dualizable. For n equals 2, so two dualizable objects are, and let me be over C here, just to make my life easier, are finite dimensional semi-simple. Yeah, this is bad. I don't want the same n. Yes, okay. And now here, Right, and now I could also choose alg2 of vect. So what do I have here? I just have commutative algebras, and then algebras which are bimodules, and then homomorphisms. And I get everything is 2 dualizable. And then for n equals 3, I would get the same finiteness conditions. But I can also be a little bit more fancy. I can put in S equals cat, k-linear. And I can do the n equals 1 case. So I take something like alg1 of, so yesterday Chris had at the board finite categories. And he told us that their result was, so that was Douglas-Schommer-Pries-Snyder, that every object is 2.5 dualizable. So we get more, right? We definitely have n equals 1, that's what our theorem says, but even more. And this is due to having some finiteness conditions here. But you could also play the game and put in something a bit weaker, like for example presentable categories. And this is, or also do alg2 of the same version. And this was in a paper just recently by Brochier-Jordan-Snyder, where they got that, well, here you have almost 2. So you have weak conditions to get to 2. And here you have almost 3 dualizability. But this really depends on kind of which version of categories you put in, which finiteness conditions you already build in. Okay, just to kind of connect to what other people have been doing. So ultimately, yes, you will want to have these higher things. We just get somehow the low dualizability, but on the other hand, we get it for all n. Let me now tell you precisely what I'm actually, make this a little bit more precise. What is alg n of S? Okay, let me start with n equals 1. So first we need, actually before I start with n equals 1, I need to recall for you what factorization algebras are, or maybe better define. The main tool will be these factorization algebras, so let X be a topological space. And I will only need X equals R or Rn. A factorization algebra on X valued in S is basically something similar to what John was talking about, a multiplicative version of a co-sheaf. So we have, in particular, an assignment from the open sets in X to my favorite S, say chain complexes, together with, for every finite disjoint union of opens in V, I have a map f of u1 times f of un to f of v, such that, first of all, I have the obvious coherence that you need to write down. second of all, this will be multiplicative. So if I have a disjoint union of two things, it receives a map from the tensor product of f of the individual ones, and that should be an equivalence. And you could also say it's a metric monoidal in a certain sense. And then the third condition is the gluing condition that I don't want to go into. So these are the factorization algebras that John mentioned, which were used by Kevin Costello and Owen Gwilliam to show that they're the observables of a perturbative quantum field theory. But we have simpler examples, namely exactly all the objects that I want to encode. So let A be an algebra, and take X to be R. Then I can define a factorization algebra on R as follows. So to every open set, to every interval, I will assign A. So to this interval, I will also assign A. And I can take a big one. I can include them into the big one. The big one is also sent to A. To every interval, I send A. And so the extra data that I have to tell you is what to do here, these multiplication maps. So I have my inclusion of two little intervals into big one. I have to give you a multiplication map. But, well, I will just take the multiplication that I have. So what this actually used was that I had R with an orientation or a framing. So somehow what you can think of this is the output of John's factorization homology A, where you take as coefficients the algebra A and the framed manifold R. And example 2, I would like to tell you, is to take two algebras and an AB bimodule M together with a distinguished point in the bimodule. I can again take X equals R, and I can choose a point P. And now my assignment will be as follows. This side, I will assign A. For any interval on the other side, I will assign B. And for any interval containing the point, I will assign M. And then similarly, if I embed this into a big interval, I will get M again, because this is again an interval containing the point. So now here I can use my bimodule map. And this also extends to a factorization algebra. So this is somehow the value of, you can think of stratified factorization homology, in the sense of Ayala Francis Tanaka applied to this guy and this framed one manifold. And those two are the ingredients to build our higher category. Let's see. More generally, maybe, I should put that here, we want to get to EN algebras. So this is a theorem of Lurie, probably also Ayala Francis, is there's an equivalence between EN algebras in S and certain factorization algebras on Rn, namely locally constant ones. What does locally constant mean? It's exactly the phenomenon that we have here. If I include a little interval into a big interval, they're assigned the same thing. So just to have this the same board, I don't have to erase locally constant U and V is an inclusion of disks, then the structure map is an equivalence. And this example over here would be an example of a constructible one. So it is locally constant, but only if you respect the stratification. So this here will be somehow our main motivation for giving our definition of this geometric approach to the Morita category. These factorization algebras show up in trying to define a TFT is maybe not so surprising if you think of Costello-Williams results, that there are somehow the observables of a perturbative TFT. All right, so let's do n equals 1. Alg1 of S. So this will be, let me just abbreviate this by y. This will be a simplicial object. It will be a Siegel space. In the sense of Toby's talk, it's just a simplicial object, simplicial space with certain properties. So what's my y0? My y0 should be my objects of alg1. So if you remember, alg1 was supposed to be the Morita category. So we were supposed to have objects or algebras, morphisms, bimodules. So how do I encode my algebras? Well, I told you over here. So here I can define this to be locally constant factorization algebras on R. So I will draw the picture somehow of the underlying space over here. What will y1 be? Y1 will be, well, I want to encode this picture. Okay, so heuristically what I will do, I will define them to be constructible factorization algebras on R together with a point as a stratified space. So I have something like this. And my two source and target maps will be given by restricting to either side.
Claudia,
Yes?
your line is oriented.
Yes. Implicitly, I always read from left to right.
Implicitly oriented, or it's oriented?
Well, the way I define it really is I take my R and then I kind of say, well, the source, I mean, P is a data. So I just say I restrict to minus infinity P. And I restrict to P infinity. So I just kind of build in the orientation for the source and target maps. But this is important. I mean, it's important which one you have.
So I'm just a little confused by the, what's the general definition of a factorization algebra on R?
Mm-hmm.
You don't, you didn't seem to.
Yes. So
Definition.
I could have chosen to define a different factorization algebra on R from an algebra by defining this multiplication to be M up. This was a choice, right?
You couldn't have a definition that forces this to be a commutative algebra. That's what I'm.
No, not in this. No, that will be that's then here. You lift this to 2.
Your UIs they're not odd, and the disjoint union is not ordered.
Yes, so there's an equivariance condition that I did not write down. Yes, you're right about that. Yes, absolutely. So this should be there's a action of the symmetric group, and it should respect that. Yeah, thank you. Okay, so now we have objects and morphisms, and for a Siegel space, I have to also tell you what the higher guys are. And what I will choose here is now I will take 2 points, P1 and P2, like this. And somehow in the rough translation between bimodules and these factorization algebras, what we had over there, we saw this you should think of as an A-B bimodule. Well, then here you should think of this as an A-B bimodule and a B-C bimodule. So this is the interpretation. So the source and target hopefully are somehow clear. You either restrict to this part or you restrict to that part over there. But I have to tell you how composition works. So in the Siegel space, the composition is encoded by this D1 map. So what's D1? I have my two bimodules here. And the factorization algebra that lives up here. And now I want to get something like this. And the neat thing is we can push forward factorization algebras. So if I have f from x to y and f is on x, then I can define the push forward of f on an open set to be f of f inverse of u. So let's use a suitable push forward to define our D1. Namely, I use the map of the underlying spaces that collapses everything in the middle to a point. So this will be my map rho. And now I put on here, I put my push forward of my factorization algebra. And somehow the way the gluing condition works, wherever it is, which I haven't told you about, is that in fact what you get here then, if you really think of the module situation, you really get the tensor product. Or actually I should say the derived tensor product if you're not working in an infinity category. So this really gives you exactly what you want from the Morita category. Composition is tensor product of modules. All right. We wanted to see something about dualizability. So let me show you for this particular example that our theorem is true. Any questions in the meantime?
How do you make sure technically that all the superficial identities hold with relating all these?
Technically what we do is we don't just add points, but actually the points are endpoints of certain intervals. And like the face maps are easy. Those are not a problem. The degeneracies are a little bit of a problem. And that's why it's more convenient to see the p's as endpoints of intervals. So then you can have the degeneracy just repeating an interval.
Construct in the other coherent functor from delta, or
Yes, yes, it's completely strict.
strict? But
Yes. Just really restricts factorization algebras to smaller parts, and that just works. Other questions so far? So for n equals 1, the only thing we have to check, the statement was that alg1 is fully 1 dualizable. So let's put in 1 here. So for fully 1 dualizable, we have to check every object has a dual. And here there's nothing to check. So let's see. We start with an object. And I will just write down the A just to remind you what this is. So I have my factorization algebra on here. So what I can do now is, this is my R. I can define a map from R to R that does the following thing. I take my line R, just this edge, I fold it over, and then I collapse. So I want to implement this fold map. Okay. So get a map from R to R, which actually does the following thing. So R is sent to something like this, and then I project. Okay. So I will call this F for fold map. So if you wish for x between, well, if this is a finite interval 0 and 1, for x between 0 and 1/2, I send it to itself. And then between 1/2 and 1, I send it to 1 minus x. Okay. And now I can push forward F. This lives on this thing. There's now a point. So what does this evaluate to? If I take a piece here, maybe I should redraw this. That's not a good picture. So here now, my point in the middle. So if I take an interval here, this is my F, and here I want to put on the push forward of F. So what is the push forward of F evaluated at this blue part? By the definition of my push forward, I have to look at its pre-image. So what is pre-image? I have a part here and a part here. And these come from two intervals here. Okay. So what these are, here I just have an A and an A. Here I have an A, but now here my direction goes in this direction, but here my direction goes in the other direction. So one copy is A and the other copy is A op. So what you can think of, this is A tensor A op. Maybe A op tensor A. Want to read from top to bottom. So what about if I touch the point? If I touch the point, then my pre-image is just one copy. So this here will be sent to just A. The pre-image of this, something in here. And what happens when I'm to the right of the point? Well, the pre-image is empty. And I did not probably write it in the best way up here. But this multiplication, actually, I should have written this for, I should have said for the empty set also you get the monodal unit. So this here will be sent to the monodal unit. So this you can think of just being as k. So what's the bimodule that we just produced by this fold map? It's A viewed as an A op times A, k bimodule. And if you've done the exercise for showing that every object has a dual in the usual Morita category, you know that this is exactly the right thing to do. All right, I know I have to rush a bit. I would just like to show you why the snake identities hold. So this construction that I just gave you was that of the evaluation map. So it's a one morphism in my Morita category because it's such a guy. It's a constructible factorization algebra. That was my evaluation map. And similarly, I can get the co-evaluation by starting like this and now bending down. So here my arrow pointed up, here it will also point up. I'm taking this part and bending down. And again, then project. And now the snake identities. I actually have to check now at this level that the snake identities hold. These are one morphisms. This is a one morphism. That is a one morphism. But it comes from something up here. And this is something I can exploit. So where the composition in the snake identity that I need to check. So remember, it was something like tensor F composed with identity tensor co-F. And this composition here comes from projection of, now I have to put them together in the right way. Of this. Okay, I stack this piece and I put this one next to it. And this thing here is very nice because you can just pull at the ends and you just get the trivial guy. So this is somehow a pictorial explanation for why after projection indeed you get the identity. So this argument, I showed you the one-dimensional case. If you want to have EN algebras instead, just think of these one-dimensional things of being a little Rn, and you do exactly that same step of folding and projecting. And for morphisms, you have a similar geometric way of seeing what happens. But since I'm out of time, I will stop here. Thank you.
So in the high-dimensional case, you use some multi-simplicial space
Yes.
which models it.
Absolutely.
So, and how, for example, in dimension 2, how does the geometry look like? Does the module lie on still on a point or along a dimension 1?
So for n equals 2, my objects will be something like this. No stratification, just a little box. My morphisms have one vertical stratum. So you can think of this side as being the E2 algebra, this side being an E2 algebra, and this side here, you still can kind of move along the E1. So it's an E1 algebra, but it's also bimodule. And a 2 morphism, now you add a point in the middle. So then you have essentially 5 interesting values, these here. And if you take the Poincaré dual of that picture, you see exactly the picture of the bygone. And then you can stack things next to each other, on top of each other, etc.
In the case of S being vect, do you know what the high-dimensional nerve or alg-n is?
What do you mean by higher dimensional nerve?
I mean, just to know, I mean, when you realize it has a space implicitly.
Oh, if I geometrically realize
Yeah,
afterwards.
yes.
I should know this, but I have to think about it for a second. I mean, it will be the analog of doing it for the usual Morita category. I mean, it will just be that, because in the example of vect, it really boils down to just having algebras, bimodules, homomorphisms. Just take the realization of this.
And when you deloop, you get back to vect.
Yes. Well, except for the subtlety that I told you about, namely these bimodules were always pointed. So actually what you deloop to is this vect star that I had written down as an example. So you get pointed vector spaces.
More questions?
So in this picture, you said you just straighten the wiggle. So it's easy to show that, like if you push forward in some respects, or if you draw this line up to
Homotopy?
yeah.
Well, you don't get the same thing, but you get equivalent ones. So, I mean, these are somehow technicalities that I suppressed a little bit, but I mean, we have spaces here of such factorization algebras, and in those spaces you allow exactly those wigglings.
Then I think we'll thank Claudia once more.